Hello students, today we are going to discuss about the Mohr circle for general case of plane stresses. So before drawing the Mohr circle, we need to know about the condition of stresses for two perpendicular normal stress accompanied with the state of simple shear. So for that, let us consider the state of plane stress in which two perpendicular normal stress are accompanied by the state of simple shear, which is shown in this figure. Here is the stress element. This diagram is showing the stress system of two perpendicular normal stress. Here two perpendicular normal stresses, sigma x and sigma y, both are tensile stresses we are considering, or like stresses or the like stresses, and the shear stress which is denoted by q. Generally, these conditions are considered in actually loaded bar, shaft in torsion, and bending beams, etc. Here you can in this figure you can see a wedge shaped stress element. Here you can see a wedge shaped stress element. We are considering this wedge shaped element as unit thickness, and these wedge shaped element are showing the condition of stresses and forces. This stress element diagram of stress element, wedge shaped element, is showing the condition of stresses, and this diagram is showing the forces. So if we resolve all the forces along AC and perpendicular to AC, we will get the final equation for normal stress and tangential stress. Here we are considering the final normal stress as sigma and shear stress as tau. So first, if we resolve all the forces perpendicular to AC, we will get the final equation as sigma AC equal to sigma x AB cos theta plus sigma y BC sin theta plus q AB sin theta plus q BC cos theta. If we simplify this equation, this is the equation we are getting after resolving all the forces perpendicular to AC. And if we simplify this equation, we will get, here is the simplification. So we will get the final equation, that is sigma equal to sigma x cos square theta plus sigma y sin square theta plus q sin 2 theta. After simplification of this equation, we will get this equation of sigma. So if we put following identities in this equation, like cos square theta equal to 1 by 2 1 plus cos 2 theta, sin square theta equal to 1 by 2 1 minus cos 2 theta, and sin theta cos theta equal to sin 2 theta, that will be 2 sin theta cos theta equal to sin 2 theta. We will get the final equation of sigma, that is sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus q sin 2 theta. Similarly, if we resolve all the forces along AC, we will get the equation tau AC equal to minus sigma x AB sin theta plus sigma y BC cos theta plus q AB cos theta minus q BC sin theta. So if we simplify this equation as we done in previous case, so we will get the final equation for tau, that is minus sigma x minus sigma y by 2 sin 2 theta plus q cos 2 theta. Here is the simplification. If in previous condition we are considering sigma x and sigma y as like forces, or sigma x and sigma y as tensile forces. Both are tensile forces. And if we consider sigma x and sigma y are unlike forces, or if we consider sigma x as tensile force and sigma y as compressive force, so we can obtain these expression of sigma and tau by changing the sign of compressive stress or sigma y. So here is the equation for unlike stresses. So sigma and tau, here is the equation. These equation we can get by changing the sign of sigma y. Now let's come to the point. Let's draw the Mohr circle for the general case of plane stress. So here let us consider the general case of the plane stress in which material is subjected to normal stresses sigma x and sigma y, which is accompanied with the state of simple shear, which is shown in this figure, here in this figure. and here all the stresses, you can see in this figure, all the stresses sigma x, sigma y and q are in this stress system we are marking as positive according to our sign conventions. We are taking sigma x and sigma y as positive. So we already found the equation for the plane stresses sigma and tau. Here is the equation for sigma and tau. So these equation are the equation of the circle in parametric form with angle 2 theta as the parameter. So if we want to eliminate these parameter, what we will do, we will square both side of each equation and we will add these equations. So we will get this equation. The final equation is sigma minus sigma x plus sigma y by 2 whole square plus tau square equal to sigma x minus sigma y by 2 whole square plus q square. Here we introduce some new parameters. If we consider the value of sigma x and sigma x plus sigma y by 2 as sigma average, and the value of r, if we put under root of sigma x minus sigma y by 2 whole square plus q square, so we will get the final form of the equation, that is sigma minus sigma average square plus tau square equal to r square. This is the final equation. So this equation is the equation of the circle with sigma and tau as the coordinate, and here we are taking r as the radius of the circle. The value of the r is under root of sigma x minus sigma y by 2 whole square plus q square, and its center as the coordinate we are taking sigma equal to sigma average and tau equal to 0. For construction of Mohr circle for plane stresses, we will follow the same procedure as I discussed in the previous cases. We will draw sigma or normal stress on horizontal axis, and shear stress we will consider as ordinate and we will draw it on vertical axis. We will take sigma is positive at the right side of the origin, and tau is positive in downward direction, and the angle 2 theta is positive when it is counterclockwise. Now mark origin O anywhere, then make OA equal to sigma x and OB equal to sigma y to the same side of the origin, because this sigma x and sigma y are alike forces, or we are considering both as tensile or positive forces. So after that, the shear stress Q is marked on the x face, or it is positive as per our sign convention. So here draw AG perpendicular to OX, which is equal to Q in downward direction, because it is positive shear stress. Similarly, make BF, which is perpendicular to OX in upward direction, because this is a negative shear stress and it tends to rotate the element in clockwise direction. So this negative shear is plotted in upward direction. Now join F and G, which is cutting at the x-axis at point C, which is the center of the stress circle, and the stress corresponding to point C will be equal to sigma x plus sigma y by 2. Since why? Because this point C is the midway or the midpoint of the midpoint between A and B, with center C and radius equal to CG. We will draw a circle, and at point C we will make CD at an angle 2 theta with CG in anti-clockwise direction. Here line CD is required as a radius vector and the coordinate of point D, which give the required stress sigma and tau. To find their value, we will draw a perpendicular DE on x-axis. So here DE will be tau, OE will be sigma, and OD will be resultant stress or sigma R. So here sigma is positive and tau is negative as per our sign convention. So here the point G, which represent the stress condition on x phase, for which theta equal to 0 and where sigma equal to OA equal to sigma x and tau equal to AG equal to Q, that is positive. Similarly, at point F, which represent the stress condition on Y phase for angle 2 theta equal to 180 or theta equal to 90, where the stresses will be sigma equal to OB equal to sigma Y and tau equal to BF, that will be negative, will be minus Q. Here we are considering R is the radius of the circle, so R will be under root of CA square plus AG square. So here is the value or the equation of the R. Now here CA will be R cos beta. From we will consider it from triangle CAG. So the value of CA will be R cos beta, which is equivalent to sigma x minus sigma y by 2, and AG will be R sin beta, that is equivalent to Q. So if we put the value of if we want to find out the value of OE, that is OC plus CE, and if we put the value of OC and CE, the value of CE will be R cos 2 theta minus beta. If we put all the values OC and CE, we will get the equation, that is sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 plus cos 2 theta plus Q sin 2 theta. This is the equation of normal stress for the plane stresses. So this OE will be equal to sigma. Here the value this OE we will consider as the normal stress. Similarly, here DE, from this triangle DE will be R sin 2 theta minus beta, and if we put the value, if we simplify this R sin 2 theta minus beta, after simplification of this equation we will get the equation sigma x minus sigma y by 2 sin 2 theta minus Q cos 2 theta. This is the equation of the shear stress, this is equivalent to tau. So the DE will be tau. So here what we will do, the DE will represent the shear stress and OE will represent the normal stress. We will we will discuss here different conditions of stress circle. The first case is when the point D coincide with point H. So here from this diagram you can see that 2 theta, the value of 2 theta will be beta. So here the value of normal stress or sigma will be maximum. So we can say the value of sigma will be sigma max, that is equal to OC plus CH. So this will be represented by this equation, sigma x plus sigma y by 2 plus under root of this CH represent the radius, sigma x minus sigma y by 2 whole square plus Q square, where the value of sigma max or the maximum normal stress is known as the principal stress, and the value of shear stress will be 0 here, and the value of resultant maximum normal stress will be maximum normal stress, and the value of angle will be here 10 theta equal to 10 2 theta will be 10 beta equal to 2q by sigma x minus sigma y. The second condition is when the point D coincide with point J. So in that condition the value of 2 theta will be 180 plus beta. So here the value of sigma will be represented by OJ. So OJ will be, we can find out this OJ by OC minus CJ. So this is the equation for OJ, and this equation represent the equation of minor principal stress or sigma 2. So we can say the value of normal stress will be minimum, or minimum normal stress will be known as the minor principal stress or sigma 2. Here the value of shear stress is 0 and the resultant minimum normal stress will be sigma minimum. The third case is when the value of 2 theta is 90 plus beta. In that condition, the value of shear stress will be maximum. So here shear stress or the maximum shear stress will be equivalent to R. So the value of tau max will be, the final value will be this minus sigma 1 minus sigma 2 by 2. The fourth case is when the value of 2 theta is 270 plus beta. So in that condition, same, the tau max will be equal to R, but it will be positive. So the value of tau will be sigma 1 minus sigma 2 by 2. So these are some cases, these are the some condition for plane stresses, and this is all about the Mohr circle for plane stresses. Thanks for watching the video and subscribe the channel for more lectures.